Welcome back. 4 exercises last time, and the first is the seed of everything we build today, so let's do it together, properly. Best line through data. Predict y as a times z. Best means smallest average squared error. Write that error as a function of the slope. Now differentiate, and yes, you may differentiate straight through an average. An average is just a big weighted sum, and derivatives pass through sums. Set the derivative to 0. We're at the bottom of a parabola in A. 2 lines of algebra. The best slope is the average of z times y over the average of z squared. Covariance over variance. This tiny recipe, right squared error, differentiate, set to 0, is the entire engine of today's video. Exercise 2. Z cubed is odd. The 2 halves of the integral cancel. 0. The counterexample stands. Exercise 3. 2 equations, 2 unknowns. An exact solve. Training error 0, even for random targets. And exercise 4. Your method proposal. Hold it up against what we build in the next 20 minutes. Today is section 2 of the paper. In full. Every formula derived, then read straight off the page. Here is the whole machine. 5 stations. 1. Collect pairs. 2. Fit the affine map with ridge. 3. Compress through a rank bottleneck using the singular value decomposition. We'll build it carefully. 4. Score per feature on held out data. 5. Verify causally inside the running model. One thing should bother you already. Station 2 fits raw coordinates of the downstream vector, but Station 4 grades feature readings. Why fit one thing and grade another? Linearity dissolves the worry. The ruler applied to t times v is just another fixed vector applied to v. Predict the full vector once, and every feature's predicted reading comes for free. 16,000 gradings from one fit. T does not map feature values to feature values, it maps the stream to the stream, and features are keyholes we look through afterwards. Focus on one downstream coordinate, one slot of the downstream vector. Its prediction uses one row of t, a weight vector w dotted with the upstream vector. The objective, the average over tokens of the squared gap plus the new ingredient, alpha times the squared length of w. The ridge penalty. Alpha is a knob we choose, why it exists, in 2 minutes. First, pause. You did the one-dimensional version an hour ago. Same recipe. Try to guess the shape of the answer before I write it. Differentiate. The fit term gives -2 times the average of x times the gap. The penalty gives +2 alpha w. Set to 0, rearrange the average of xx transpose, that's the input covariance matrix, plus alpha times identity times w equals the average of x times y, the input-output covariance. Invert. Look at it next to the homework answer. Same formula. Covariance over variance, except variance is now a matrix, covariance is a vector, and alpha has been added to every diagonal entry of the variance. One more step. Each of the 2,300 downstream coordinates gets its own w by its own copy of this formula. They don't talk to each other. Stack the rows, that's t. 2,000 independent little regressions wearing one coat. Remember that. The singular value decomposition is about to tie them together. And the shift, b? You may have noticed both derivations began with assume everything is centered. Subtract the means. That's not a dodge, it is the answer. Fit t on centered data. Then ask what constant fixes the means back up. B equals the mean downstream vector, minus t applied to the mean upstream vector. The intercept is bookkeeping for the means, computed after t, in one line, exactly like the intercept of a school regression line. Now alpha. Recall the spectrum from video 2. A few loud directions, thousands of quiet ones. In one dimension, the ridge answer is average of xy over average of x squared plus alpha. Watch the denominator. Loud direction, variance 9, alpha 0.1, Alpha is a rounding error. The data decides. Quiet direction, variance 0.01. And here's why that's dangerous without alpha. You are dividing by a tiny number that is itself mostly measurement noise. Tiny, noisy denominators produce huge, unstable answers, a slope that flips sign from sample to sample. The fit doesn't know it's guessing. It confidently amplifies noise. And on fresh data, confident noise is poison. Add alpha. The denominator is now at least alpha, the division is tamed, and the weight glides towards zero instead. The philosophy of Ridge in 5 words: when unsure, say 0. Who picks alpha? Not the training error. Smaller alpha always fits the training set better. The training set would vote for overfitting every time. The paper does it the standard, honest way: 5-fold cross-validation. Split the training data into 5 slices, 5 times over, fit on 4 slices, and grade each candidate alpha on the 5th. Average the 5 grades, keep the alpha with the best average, and the final test slice, 20% of everything, is touched exactly once, for the results you'll see in video 5. Before we compress anything, an objection you should be raising. Video 1 taught that layers only add. The downstream vector is the upstream vector plus delta. So the input is literally sitting inside the target. Doesn't the do-nothing map, T equals identity, predict no change, already score wonderfully? Yes, it does. On raw coordinates, identity captures every part of the stream the layers didn't touch, which is a lot. That is exactly why the paper grades through the keyhole, per feature, on tokens where the feature fires. Along DF, at firing moments, the question is whether the feature's value is predictable, and identity only wins if the feature genuinely was already present upstream, which is precisely the thing we're trying to detect. So identity isn't a bug, it's the null story. Transported means it was already there. The learned T gets to beat it by also capturing rotations, rescalings, and mixing. Transport with a change of clothes. Keep identity in your pocket as the baseline mental model. Now the compressor. The singular value decomposition is a theorem. Every matrix, any shape, any entries, is 3 simple moves glued together. Rotate the input space to a special set of axes. Scale along each of those axes by a non-negative factor. The factors are sorted. Biggest first, and they're called singular values. Rotate the result into the output space. Rotate, scale, rotate. Concretely, each singular value comes with a pair of directions. An input direction, listen to this pattern in V, and an output direction, write the result along this pattern, with the singular value as the gain between them. A matrix is a bank of independent one-dimensional channels. The bottleneck is now one sentence. Keep the R strongest channels, 0 the rest. That's T sub R. 2 fair objections. First, is chopping legitimate? Eckhart and Young, 1936. Among all rank R matrices, the truncation is the closest one to T in total squared error. Chopping isn't a hack. It's the optimal projection of our fitted map onto rank R. Second, why fit full rank and then chop? Why not fit rank R directly? Because direct rank R fitting is a hard, non-convex search, while Ridge has a one-line closed form, and the chop is instant. And because we want the whole ladder of ranks, 1 through 2000, and truncation gives every rung from a single fit. Note also the division of labor between our 2 knobs. Alpha fights estimation noise. It's hygiene, tuned once by cross-validation. R is the measurement, the size of the channel, and we don't tune it. We sweep it and read the curve. Same mechanics, opposite purposes. And that sweep is where the science lives. For each feature, walk R upward and watch held-out prediction. Now we can finally pin the series vocabulary to numbers. Call a feature transported when its per feature R squared is high, near 1 at some rank, and the causal check passes. Call it synthesized when even the best linear map leaves its R squared low. The reading simply isn't a linear function of the upstream stream. The layers in between manufactured it. The boundary is a judgment call. The paper shows full histograms rather than one threshold, and you'll read them in video 5. If a feature is well predicted already at rank 50, its transport lives in a 50-dimensional channel. And how high the curve could go at each R, that ceiling has a closed form. Video 4 derives it from scratch. Station 1 hides a decision. A pair is upstream at position I, downstream at position J. Which J? The paper's choice, the simplest, is J equals I, same token, straight up the stack. What that policy cannot see, attention moves information sideways. A feature could be carried, perfectly linearly, from token 5 to token 9, and same token pairing would look straight up, find nothing, and file it as synthesized. So the results are a floor on transport, not a census. Whatever the same token policy finds is really there. What it misses might be transport traveling diagonally. Richer policies follow the strongest attention edge, paired delimiters, track copied tokens are named as future work. Second decision. Which features enter the grading? Gemascope offers 16,000 per layer. Many are dead or redundant. The paper filters to roughly the best 5%, features that fire at least 10 times in the test data, look semantically coherent, and carry real causal weight. Honesty check, because you should be suspicious. Every statistic in video 5 is a claim about these well-behaved features, not about all 16,000. That's a scope limit stated plainly in the paper's appendix. One more subtle choice: each feature is scored only on tokens where the true downstream feature is active, because on the vast majority of tokens a sparse feature is simply off, and grading mountains of zeros would flatter everyone. Here's the appendix paragraph. Data split filters, read it. Prediction on recorded vectors is spectator science. Station 5 puts the map inside the running model. Let's be surgical about the surgery, because the details matter. Run the model on a text. At the upstream site, layer L, position I, delete the residual, zero it out. Let the model keep running. Layers L through L plus K-1 now compute on a whole. Yes, neighboring positions attending to that token see the whole too. That corruption is part of the experiment, and every run we compare will suffer it equally. Then at the target site, layer L plus K, same position, overwrite the arriving vector with our reconstruction. TR times the deleted upstream vector, plus B. Overwrite, not add. We're replacing the stream's answer with our map's answer. From that layer on, the model runs purely on what our linear map carried. If the feature's reading and the model's output quality survive, the map carried what the model actually uses. Survive. Compared to what? A third run sets the floor. Same deletion, but at the target site inject nothing. Leave the zeros. Why is 0 the right floor? Because it's the no information intervention. Whatever the stream carried to that site is erased and replaced by silence. Our map must beat silence. Any restoration above the 0 run is information the map carried. 2 gauges are read. Gauge 1, the feature lamp. Does the downstream feature reading return to its clean value? Gauge 2, whole model behavior, perplexity, how surprised the model is by each true next token, averaged over held out text. The paper uses 100 sequences of 256 tokens. Perplexity 1 means perfect prediction. Higher means more confusion. The 2 gauges answer different questions, one feature versus global behavior, and the paper reports both. Clean run at the bottom, 0 run at the top, and the surgery run lands somewhere in the bracket. Where it lands is the causal verdict. Step back and see constraint 2, built into hardware. R squared on held out pairs certifies the form. The relationship is linear. Ablate and inject certifies the reality. The model runs on what the map carries. Either alone can mislead. Together they say, transported, and it matters. You now own every station. Proof. This is the paper's own figure 1, their schematic of the entire method. Left, the residual stream, and the operator bridging layer L to layer L plus K. Middle, ground truth residual above, predicted residual below. Right. Both are pushed through the SAE decoder directions of the activated features, the keyholes, and compared, feature by feature. Matched readings, transported, mismatched, synthesis. Top to bottom, there is nothing in this figure we did not build with our own hands today. Homework. All 3 feeding video 4. 1. Rederive ridge blind in the expectation form we used. Then answer, what does W star become as alpha goes to 0, as alpha goes to infinity? 2. The matrix with rows 3, 0 and 0, 1. Write its singular values, truncate to rank 1, and compute the squared error you accepted by chopping. 3. The setup for next time. Someone hands you the best possible rank R linear predictor of the downstream stream. What quantity about the 2 streams would let you state it's R squared without fitting anything? Sit with that, because the answer, a number per channel, computable in advance, is the ceiling. Next time we derive it from scratch, whitening, canonical correlations, and the formula from the cold open of video 1.